All right, what we're going to talk about in this video is we're going to learn how to simplify higher index roots. All right, so what does that mean? Well, we're already familiar with simplifying a square root. So what we're going to do is we're going to simplify a cubed root. Okay, we could simplify a fourth root. We could simplify a fifth root. Again, it's this little root number right here that we call the index number. And really, we could continue this on and simplify what comes to be known as an nth root, meaning that really the index number can be anything. And so there's going to be two parts to this mix. And so the first part I'm going to do right here in example 1, and we're going to learn just how to simply simplify just a number underneath a root, okay? And then what we're going to do with example 2, part 2 of these notes, is we're going to simplify with a variable expression. All right, so what I'm going to do here for part A is I'm going to start with something familiar so that we can build on this concept. So if I was simplifying the square root of 28, I would go get my calculator, which, by the way, if you want to hit pause, go get your calculator so that you can work through this with me. And I would start listing out some perfect squares. Okay, so perfect squares are going to be 1 times 1. Well, we probably need to put that one. 2 squared. 3 squared, 4 squared, 5 squared, 6 squared, 7, 8, okay, 64. And we would keep going, and then we could even go on to say 9 squared, and we could keep going. So really, what our job is to find the biggest perfect square that goes into 128. And so if I look at my list, I know 81 doesn't work. I'm going to actually go through my list backwards because I want to find the biggest perfect square. And what I will find is that 64 right here is the biggest perfect square. So what we do is we split this into the square root of 64. Now here's where I need you to pause for a second, get your calculator. Let's take 128 divided by 64, and we find that it is in fact 64 times 2. So split it into square root of 64, square root of 2. Well, since square root of 64 is a perfect square, this becomes whole number 8, and we're left with a square root of 2. So that should be nice and familiar. Let's build on this concept, and let's change the square root into a cube root and see how the process changes. So I'm going to start in a similar way. It's just instead of listing out my perfect squares, I'm going to make a list of perfect cubes. And so again, this is just a matter of making a list and utilizing your calculator. 2 to the third power is 8. 3 to the third power is 27. 4 to the third power is 64, and 5 to the third power is 125. All right, so there's really no need to go any bigger because all of those are over 128. So when I look at my list, 125 doesn't work, but I see right here, as we saw in part A, that 64 goes into 128. So when I split this, it's the cube root of 64 times the cube root of 2. Now it's really important here that we make sure we put the index number because it's going to simplify differently than it did in part A. So what I see here is since 64 is a perfect cube, when we take the cubed root of 64 and go backwards, that will give us whole number 4. So this is the whole number 4 with a cube root of 2 left over. All right, so you can see how that answer changes based on how I change the root. Well, I'm going to go one more example in this set, okay? And let's change the cubed root into a fourth root and see how that changes the process. So what we're going to do is we're going to put out our perfect fourth roots, right? So we just get the calculator. We say 2 to the fourth, type that in, and you'll see it's 16. 3 to the fourth, if I type this in, is going to be 81. 4 to the fourth, we're at 256, it's too big. So there's no point in writing those down. So the bigger the root gets, the less numbers we usually have to write out just because it gets big so quickly. So when I start going through my calculator, 81's not divisible, but I do find that 16 is. And so when I split this, it's the cubed root of 16 times, I'm sorry, I think I said that wrong. It's the fourth root of 16 times. Now I'm pausing because in my calculator I'm taking 128 divided by 16, and I see that it is 16 times 8. All right, so again, which one of these is the perfect fourth root? Well, if we go backwards, the fourth root of 16 takes us back to the 2. So this becomes whole number 2, and we have a fourth root of 8 left over. All right, so that is what we did one day, was just practice simplifying these. I'm going to throw in one problem on your own before we move on to the next section. So what we did in class is I then gave students, and I said, all right, we're going to simplify the fifth root of 6,144 divided by 2. All right? So when I look at this, you can go ahead and take a minute and write this down. Often what happens, the student's eyes get kind of big and it looks a little intimidating, but we got our calculator. Let's take this step by step. First thing I need to do is, I think we can divide that, right? So let's right off the bat, let's take 6,144, take that in your calculator, and let's divide that by 2. And right away, I can make that number smaller just by simplifying that fraction first. So, same thing. I go in and I start writing out my perfect fifth roots. I don't know them off the top of my head, so I just make a little list. 2 to the 5th, type it in my calculator, I see it's 32. 3 to the 5th power, type it in my calculator, it's 243. Since we're all the way up at 3,000, I think we need to go a little bit bigger. 4 to the 5th power is 1,024. By the time you get to 5 to the 5th, you're over the number, so we can go ahead and stop. So now it's really just a matter of start with your biggest number and take 3,072 and divide by each of these perfect fifth roots. All right, so go ahead and play around on your calculator for a minute. And what I'm finding here is that 1,024 is divisible. So when we split this, it's the fifth root of 1,024, and it's going to be times by 3. Okay? So when we look at this, what is the fifth root of 1,024? It's going to equal whole number 4 with a fifth root of 3 left over. All right, so there's really nothing that I can throw at you that's going to be much harder than that. That's the idea of how you simplify roots with different index numbers. Now, our second example is where we're going to take the same idea and we're going to simplify variables. We're going to simplify expressions. So example 2, this is kind of like part 2 of the notes, and we're going to simplify expressions. All right. So for the first example, what I want to do is let's look at, for part A, let's look at the cubed root. Let's keep doing that. Sorry about that. All right, the cubed root, and I just, of 27 x to the 5th y squared z to the 6th. All right, and I have to be honest, this problem looks way more intimidating than it's really going to be. So there's a couple different things that we need to know going into this example. So I'm just going to put over here, I'm just going to put recall so that we can use this to apply to how we're going to do part A. What would we get if we took the square root of x squared? Well, we talked about how the square and the square root cancel, and the reason for that is because this is a second root and it's a second power, and they cancel out, and this is just going to simply equal x. All right, let's do a couple more and see if we notice a pattern. What happens when we cube root x cubed? Well, the cubed and the x in the third power cancel, and we get x. What happens when we fourth root x to the 4th? It's going to cancel, we get x. So here's what I'm noticing is that if it's a square root, every group of 2 x's will simplify to be x. In a cubed root, every group of 3 x's will simplify to be x. And in a fourth root, every group of 4 x's simplify to be x. Okay? So let's keep this in mind when we're doing this problem right here. Now what I'm going to do is I'm going to write this problem out, and we're going to kind of do this the long way. So, and then I'll give you a shortcut, and we can do these a little bit quicker. So this is going to be 27. X to the 5th, I'm going to expand out to be 5 x's, right? Y squared is going to be y times y, and z to the 6th means that there are 6 z's multiplied together. 1, 2, 3. Okay, so I think I got all my variables here correctly. And so really what I'm trying to do is I'm trying to show you the why it simplifies this way. Like I said, shortcut is coming. All right, so what's going to happen is some of the terms are going to be outside of the radical. Some of the terms are going to be left over inside of the radical. So the first thing I look at is I see 27, and 27 happens to be a perfect cube. So when we simplify the cube root of 27, that's going to equal whole number 3 on the outside. All right. Now, when you cube root the x to the 5th, I've expanded out my x's. Every group of 3 x's simplify to be an x. So how many groups of 3 can we make? I can pull out one group of 3, and then what's going to be left over here is we're going to have an x squared left over. Now, let's look at our y's. How many groups of 3 can we make? Well, we don't have enough, so we're going to leave y squared underneath. You need at least 3 y's to be able to pull one out. All right, let's look at our z's. How many groups of 3 can we make? I see one group of here, and I see one group of 3 here. So these group of 3's is going to simplify, and these group of 3 are going to simplify. So what I'm going to say is I can pull out 2 groups of z's. All right, so what the final answer ends up looking like is 3xz squared with the cube root of x squared, y squared left over. All right, so what are we really doing when we're making our groups and circling them? What we're doing is we're dividing, okay? So what we're doing is we're basically saying 3 goes into 5 one time with 2 left over. And we say 3 does not go into 2, so that's why we didn't break up the y's. We say 3 goes into 6 2 whole times with nothing left over. So when you take a root, when you cube root variables to exponents, we're really just dividing. All right, well, let's see if maybe we can try one more example and maybe use our division property to do this a little bit easier and see if this makes more sense. All right, so we've got 5th root of a to the 4th b to the 20th power times the 5th root of 4a squared b. All right, now, first thing is this looks a little different, okay, just in that we have 2 separate 5th roots. Well, as long as it's the same type of root, as long as they're both 5th roots, we are allowed to multiply this together and condense it into a single root, okay? So let's go ahead and multiply our terms, and let's make this, all right, let's make this here, sorry, it keeps erasing. Let's make this the 5th root. All right, 16 times 4, type in my calculator real quick, is going to be 64. When we take a to the 4th times a squared, that's going to give us a to the 6th power. And then finally, we're going to take b to the 20th times b, and that's going to condense to be b to the 21st. So really, we do have a problem like example A. We just had to multiply our roots together first. All right, so here's what's going to happen. First, we need to simplify the 6th root of 64. So I would come over here, and I would make a little list of my perfect 5th roots. I got 2 to the 5th power. 3 to the 5th power is too big, so I'm not even writing it down. So this splits into the 5th root of 32 and the 5th root. Well, how many times does 32 go into 64? 2 times. So when I simplify this, I'm going to have some parts on the outside. All right, we're going to have an outside part, and then we might have some terms that are left under the radical out here. Well, the 5th root of 32 is a whole number, so we're going to put the 2 on the outside, and we're going to have a 2 left over. Okay? Now, let's do our variables. We're going to say that 5 goes into 6 how many times? 5 goes into 6 one time with 1 left over. What you're doing, again, is we have 6 A's underneath this 5th root. 1, 2, 3, 4, 5, 6. How many groups of 5 can I make? We can make one group of 5. We can make one group of 5, and that's why I pulled out an A with one single A left over. It's division, okay? So now I'm going to say that 5 goes into 21 how many whole times? Well, 5 goes into 21 4 times with 1 B left over. All right, so our answer is going to look like 2ab to the fourth with the fifth root of 2ab left over. And we'll practice this more, but that's really the idea. Honestly, the variables are probably easier than the numbers. We just need to get the hang of it. All right, so last problem here. Let's end with part C. And what if we are asked to take the cubed root of x squared? Oops, just keeps erasing. I apologize about that. Cubed root of x squared, and we want to times that by the square root of x. All right, well, the problem is you must have the same type of roots. Must have the same type of roots, meaning cube roots can multiply, square roots can multiply, but you can't take a square root and times it by a cube root. So you must have the same type of roots. So here's what we're going to do is we're going to apply what we've learned about changing this to an exponent. So I can rewrite this in exponent form if I make it x, and what we learned is that the power is the numerator and the denominator is the root. The cubed root of x squared is the same thing as x to the 2/3. And we can change x to an exponent. This would be like having the first power, and this root is assumed to be the second root. So this is going to change to be x to the 1/2 power. And now we can use an exponent property that if we have x to the a times x to the b, that the base stays the same and the exponents get added. So what this is going to equal is base x, and I'm going to go over to my calculator and we're going to add the exponents, and I'm going to have the calculator help me out. I'm going to type in 2/3 plus 1/2, and that gives me, and then we're going to hit math frac, right? Math, enter, enter, and this is going to be x to the 7/6 power. Now, the general rule is if the problem starts in radical form, then we're going to give this answer in radical form. And the way we convert this back is this becomes the 6th root of x to the 7th power. Okay? One little last simplifying thing. 6 goes into 7. We have more x's in here. We can make a group of 6. 6 goes into 7 one time, and we're going to have 1 x left over. Okay? So what that is, illustrated out, is we have the 6th root with 7 x's underneath. 1, 2, 3, 4, 5, 6, 7. And we can make one group of 6, so that's why I pulled out 1x with a single x left over. Okay? So that's the kind of stuff that we're going to also apply if we don't have the same type of root. All right, so hopefully you got all of that down and that helped a little bit catch up on what you missed in class. Thank you.